Hello, everyone, and welcome back. We're picking up where we left off, talking about binary trees, and we're going to go one step more categorically deep, I suppose, and discuss binary search trees. So just a quick reminder of what our binary tree class would look like at a default. We have our binary tree, just like it used to be a linked list with a single root node. We call it root now because of our tree terminology, but it really is just like our top node from before. And then rather than having a single pointer to .next, we have two pointers because we have two nexts that we could potentially have. We have a left and a right. Working with that, let's see how we can implement a binary tree or a binary search tree. So a binary search tree follows the definition of a binary tree with one extra constraint. So a reminder that we started with a tree definition, then we moved to a slightly more constrained binary tree definition, and now we go to a slightly more constrained binary search tree definition. Now for the binary search tree definition, we'll notice that these values actually matter now. We let X be any node in the above binary tree. We can observe that all data in the subtree rooted at X, that to the left, the data to the left will always be smaller than the root, and the data to the right will always be larger than the root. That's always going to be the case, and we're going to assume that we don't have duplicate data in these types of trees. As long as this is true for all of our nodes, it satisfies our binary search tree property. This isn't written in a particularly mathematical or recursively defined way, but we'll see the recursive definition in a minute, and it matches up with this. We'll notice that one is a root, or is a root of its own tree, and it has no children. It's a valid binary search tree. We'll see that 2 has children, and all of the children to the left are smaller, and all the children to the right, there's none. So we can see then that this is a valid subtree. We can also say that 4 alone is a valid subtree. We can then move our way up to 3, and we can see 3, everything to the left is smaller, everything to the right is bigger. So we can see that this is also a valid subtree, a valid binary search tree. And we can do that on the other side as well. We have 2 leaves. Both of those are valid trees. We can look at the tree with 8, rooted at 8. We can see that to the left we're smaller, to the right we're bigger. We can look at the tree rooted at 6 and see that everything to the right is bigger and that there's nothing to the left. And then we can look at this overarching rooted at 5 and see everything to the right of 5 is bigger and everything to the left of 5 is smaller. So this is indeed a binary search tree and satisfies the binary search tree property. Now, often we're going to write this as BST because binary search tree is sort of long-winded. So just something to remember. The subtree rooted at any node in a binary tree is itself a binary tree, as we just saw. So our recursive definition in a more formal context would be a binary search tree is either a single node or it's a binary tree such that the left descendants are less than the roots data and the roots data is less than the right descendants. So it always follows that pattern. So, and such that the subtrees rooted at root.left and root.right are also binary trees, right? Everything has to be binary trees or binary search trees all the way down. Okay, so the binary search tree is a data structure. It's not an ADT. There is a difference. It is a data structure. We are talking about, we're not talking about behavior at this moment in time. We're not talking about what it stores. We're talking about how it stores it, right? So we're storing it in a tree structure. This is a data structure, and it can be used to implement our table ADT. So rather than using a hash table as we did previously, we're talking about a different way of storing our data. So we used an array data structure to store our table ADT previously. Now we're going to use this data structure to store our table ADT. Now we can define our insert, search, and delete operations, which we will do shortly, and we will find that they're all better than an array, slightly worse than a hash table, but not terrible. And we can actually do the traversal of the tree in order, which we couldn't do with our hash table. So we can have a print operation as well. When we tried to do it with our hash table, we ended up with n log n at our best. And here it will be significantly better. So let's start by looking at a binary search tree, and you'll take my word for it that this is a valid binary search tree. We can always check it by making sure that everything to the left of a given node is smaller and everything to the right of a given node is going to be bigger. And as long as that's true for every single node, and that no node has more than two children, we know that we have a valid binary search tree. Now, when we look at this, we can sort of visually determine how to find our minimum entry in the tree. When I look at this tree, I can sort of just see, well, I know everything to the left of this is going to be smaller than it. Everything to the left of this will be smaller. And I sort of just keep following that pattern and I'll find the smallest value right here. And what that actually means is that finding the minimum entry in a binary search tree, it will always be our leftmost child. Our leftmost leaf is the minimum, and that's always going to be true. And by that same logic, we can figure out how our maximum entry can be found as well. And what we realize is if we know that we're always going to be moving to the right to find something bigger than us, we're going to keep going until we can't move to the right anymore. So our rightmost child, our rightmost leaf, will always be our max value. Okay, so to find the minimum, we just kept moving left until we reached a node that didn't have a left child. And we can think about this pretty recursively because just like traversing a linked list, we're just going to keep moving in the same direction until we can't move there anymore. So the code is lower down, but for interaction's sake, I'll write some of it here as well. Imagine for a second that we had a function like get minimum, and it would be called on our root node the very first time that we call it. And very simply, if cur.left is not null, we should go down that pathway. Return get min cur.left. If it is null, we are the leftmost child, else we can just return our data. There we go. Didn't leave myself a ton of room. That's sufficient. Okay, so here it is, also recursively defined. It's exactly as we said. You don't actually need an else. You could just like pull this back out. The else isn't necessary, but it's technically more correct to show the else there anyway. So pretty straightforward. If we here we write it in terms of the base case first. This is the base case, and then this is the recursive case. Whereas in my code, this is the recursive case, and this is the base case. But it's in one, half a dozen in the other. Both are perfectly acceptable. On your own, you're now able to write this recursively as a maximum function as well. Once we get a little bit further and are able to actually do inserts into our tree, you'll be able to test them a little bit more. You can also rewrite both of these functions, while maybe not testable at this moment, to be iterative instead of recursive. And it's a great exercise to walk through if you're looking for something to do. Okay, let's talk about the search operation on the binary search tree as well. So when it comes to the search operation on a binary search tree, it's pretty similar actually to what we just did. So here we did a search, but we weren't searching for a particular value. We were searching for the minimum. We just wanted to keep going until we found the minimum. Our search is very similar. We're going to start up at the top and we're just going to go looking for the value. And we know if we should go down the left path or the right path, depending on the node that we're looking at and its relation to the value that we're looking for. So algorithmically, if we were looking for the value 32, we would start here and we'd recognize that 32 is bigger. So we need to go this way. And as long as we can go this way, we do. Same thing here. We go to 27, realize that we're not equal to 27. We're bigger than 27. We can go right, so we do. We'd hit 36. We'd realize that we are smaller than 36 and we can go left, so we do. And then right here, we'd find 32 and we could say true, we found it. This is really just a search of finding it or not. So true, we found it in this case. So we just sort of follow the pathway all the way through until we find the node we're looking for. What happens if we are looking for a value that maybe isn't in our tree? Instead, let's look for 33 so that we could follow the same path. We know that we need to go bigger than 18. We know we need to go bigger than 27. We know that we're smaller than 36, so we go over here. We know that we're bigger than 32 and we're looking for 33. So we try to go to the right, but nothing is there. If we hit a null, we know that our value we're searching for is not in our tree. So we can say false, it's not in the tree, it's not contained there. Within these notes, you'll be able to sort of walk through the example that we just did there to find our value. And of course, we can follow up as well with a failed search. This one looks for 14 instead, where it will go 18 to 12 to 15 to null, trying to go left null. Really great exam questions look like this, where I ask you to tell me the path that a node, that the algorithm might take in terms of lefts and rights until it either finds it or doesn't find it. So there's some great exam questions in there as well. So the search algorithm is really straightforward to implement iteratively or recursively, but doing it recursively doesn't really give us anything for a search algorithm. We can, but it's just not really necessary in this case. Recursion, as always, is a little bit trickier to follow, so we only use it if we really need to. To finish off this review video, we're going to talk about the insert as well into a binary search tree, and then in the next video, we'll sort of finish off inserts and deletes as well. So when we add a new entry to a binary search tree, we have to make sure that we preserve that binary search tree property. Now, the thing is, of course, if root is null, it's pretty straightforward, because if root is null, we just equals. We just make a new root with our data, right? That shouldn't surprise any of us with our data. And that's pretty easy for us to understand and follow. However, if our tree already has a root node and potentially has other nodes, we need to go and find the correct spot to put our value into. So since we know that 14 is not in here, let's just pretend for a second that we wanted to do an insert of this value 14. So what we would do is we would actually start our traversal right here, and we would do a comparison, and we'd see that 18 is bigger than 14, so we'd walk down the left side. Here we'd see that 12 is less than 14, so we'd walk down the right side. Here we would see that 15 is greater than 14, so we would attempt to walk down the left side, and we would see that dot left of 15 is null, which tells us that 15's dot left should be 14. So the steps that we took were compare to the cur data, determine if we're going left or right, if left/right choice is not null, walk the path, and I'm going to run out of room. If our left or right choice, whichever one we needed, is null, set that left or right choice to the new node. And that's all there is to it. So it's just a search. We just are looking to find the correct spot. If we find a node that equals the new node data, we don't add it because we are assuming no duplicates. Okay, so here, imagine we're going to add the value 30. I'll go ahead and I'll put it right here. I'll walk through it like with that same sort of obnoxious animation, and then the slides will follow through as well. So we'd start off right here. We'd see that 30 and 18 are not equal. 30 is greater than 18. So we would walk this way because there's a path to walk down. We'd see 27 and 30 are not equal. We'd see that 30 is greater than 27 and that we can walk to the right. So we do. We'd see that 36 and 30 are not equal. We see that 30 is less than 36 and that we can walk to the left. So we do. We'd see that 30 is less than 32, right? They're not equal. And when we tried to walk to the left, we'd see we'd hit null, which tells us that 32 dot left should be equal to our brand new node. And we would get an insert right there. We can watch that same thing sort of follow through by following this red highlighted node to tell us when we do find our new position on where we put our node, we go ahead, we slot it in, and we're maintaining that tree property. All right, we'll do another example of insert in my next video. We'll also do a delete, and then we will do some of the different types of traversals before we move on to discussing the algorithmic complexity of binary search trees and other types of trees. Thanks everyone for joining me, and I'll see you next time.